right, good afternoon. It's 1:30, so let's get started. I know some folks are still coming back from lunch, but in the interest of time, we should get this going. So this is a multi-scale MIT dynamics session. We know this room is big, so for those of you who are sitting in the back, please come forward. This room is just too big for just a single session to have a good discussion. So if you're comfortable, please come forward closer to the screen. You don't need to feel shy. You are not asked to give comments, but you're encouraged to. But anyway, please be an active part of the session. So here's the schedule. So the first half of the session is devoted to focused discussion of the highlight and high resolution convection, particularly high time resolution convections. So Daniel will talk more about the details, so I don't spend too much time on describing what that is. But recently, the SuperDAN Canada had campaigns of having a much higher time resolution measurements than previously possible. So that opened up the window for providing high time resolution convection. So we'll dedicate good amount of time for this session. And then we have 3 contributor talks. So as you can see, so we intentionally reduced the number of speakers so that we can have a good discussion. So this session is not like DayU style session, but it's really a workshop discussion-oriented session. So if you have any comments, questions, even from basic, don't be afraid of raising hand and asking comments. We do have a lot of time for Q&A. And also, one announcement is that, we'll probably see this pretty soon, but there are related sessions in the fall AGU meeting. So particularly the MIT coupling the cross-regional space we are leading, but there are also a good number of good sessions, including the current system sessions and tail Aurora connection sessions. So if you are going to fall AGU meetings, please do consider these sessions. Okay, so without further ado, let's get into this discussion of the high time resolution convection. Well, the first speaker is Daniel Billet. He will tell us about what this campaign is, what kind of exciting data we are getting.
Yeah, hi everyone. I'm Dan. I work at SuperDAN Canada, and I guess I'm going to introduce some of the work that, not me, some other people, well, some of it's me, but like it's really building off the foundation of some work that's been built over the last 5 to 10 years to really improve our data and like get some more out of what SuperDAN is technically capable of. So a lot of people will know what SuperDAN is. But to just give like a high-level overview, it's this network of high-frequency radars that is all around the world. That works kind of well. There's just about 40 radars now, all covering the northern and the southern hemisphere to a lesser degree, just because there's less land there to put a radar on. And we're measuring the high-latitude ionospheric convection, so the ionospheric footprint of the magnetospheric Dungy cycle with reconnection in the day side and then reconnection in the night side. That's what we're measuring here, and this is kind of like the bread and butter data product that SuperDAN's been producing for the last 30 years, this convection map. I work at SuperDAN Canada, which is basically responsible for these 5 radars shaded in red here, and that's going to be the focus of this presentation and also kind of like the data that's being used in the next few presentations. So SuperDAN Canada, 5 radars, Saskatoon, Prince George, Inuvik, Clyde River, ranking in the very popular radars because they're high latitude and polar, so they get a lot of good like auroral and polar cap data. Over the last 5 to 10 years, these radars have been drastically upgraded. The old system is based on like nearly 40-year-old hardware, analog, very difficult to work with, make new experiments with, take advantage of new innovations in radio science. So that's been upgraded. We now use software-defined radios, and the high-level benefit of that is we now have much greater control of all the experiments that we can do. And to give an example of what we can do, first I'll take a step back and tell you about what we used to do and what we still do going forward, but this is kind of traditionally how a supernova radar operates. Nominally, we scan in 16 beam directions, one at a time. We go on one beam, we linger for about 3.5 seconds, and then we go to the next beam, and then we go on and on that. We transmit and receive each one individually. And that's using this very narrow beam pattern where a lot of power is sent out in a very specific narrow direction. And then we just electronically steer that across the phase array to get all these directions in the entire field of view, which is quite large. This is like several, almost like 1 million square kilometers. A new way that's been enabled by the software-defined radios, now that we have this antenna-level control of all of them, is instead what we can do is just light up the sky with radio waves and then receive the whole field of view all at once. And then all this old-style beamforming that was being done one at a time, that's now all done in software after the fact, which is really cool because you can just go back in time and kind of like make however many beams you want, or like change the integration that you were using in the experiment. So this in itself is already very flexible, but the immediate impact of that is by receiving every single beam direction at once, we just automatically get a 16-fold temporal resolution improvement to the data because we're now not doing one beam at a time, we're just doing them all at the same time. So we've gone from 1 minute per scan, 3.7 seconds per beam, to 3.7 seconds for the entire scan. And this is what the data looks like in practice. So this was like an interleave experiment from a couple years ago, where on the left, we were just using the old style narrow beam transmission. And so that was going one beam at a time. And then in the next integration, it would do a wide beam, which is this on the right. And then it would go back and then do another beam on the left. And then it would again do a wide beam. So this isn't quite the highest time resolution we can get because it's going back and forth between the two modes. But this on the left is updating every 2 minutes, and this on the right is updating every 7 seconds. But this gives you an idea of like the improvement in temporal resolution that we get without sacrificing spatial coverage of the radars. That's the biggest deal here. We're not losing any the spatial coverage, which is really important for the wide field of view of all the supernova radars. So where I come into this is, well, I've used convection patterns for a lot of my like relatively short academic career. What if we could take all that new high time resolution 3.5 second data and make something like this, a supernova convection pattern, which is nominally made every 2 minutes, and instead do that every 3 seconds? Well, that will open the door to a lot of physics, right? Because right now, a lot of the fancy, like fashionable physics that is happening on very short timescales, ionospheric dynamics that last on the order of seconds, that kind of science was limited to satellites, or if you were doing it with supernova, you'd pick a single beam and just linger on that beam, or maybe like a couple beams to spread it out a little bit. So this just kind of opens the door. If we made like convection maps like this for every 3 seconds, that would just give us a lot more new things that we could do with physics-wise. So I won't go into details with how I've made these convection maps. They've used a local spherical elementary current system fitting method called LOMPA, which is made by Carl Landau over in Norway. But this is just the product. This is convection maps every 3.5 seconds using the Supernova Canada wide beam data. And you can see from just these plots that there's a lot of variability in here. These are updating. I sped these up, but they're updating every 3.5 seconds. So you can see there's a lot going on that we would have just missed if we were updating this every 1 minute or every 2 minutes. And then I've done some comparisons with satellite data just to make sure we're kind of still seeing the same thing. One thing to note is we don't solve the inherent issues with supernova radars. They still underestimate the ionospheric flows a little bit. And this is still a fit, so there is still a degree of smoothing going on when we try to connect all the velocities together. But broadly, this is Swarm B on the left, and this is DMSP, cross-track velocities on the right. We're still getting the same. We're still measuring the right ionosphere, to put it that way, and the data looks good. And the way I've shown these plots is these darker vectors here, and there's less dark vectors. those are where we have supernon data. So in this field of view, which is, several million square kilometers over northern Canada, Greenland, and the polar cap, we're saturating this region with data because the Supernon Canada radars fill this entire region. So it's a pretty nice region to fill with the radars because, like I said, it's the high latitudes. It's from the auroral zone all the way up to the pole. So we get the cusp. We get polar cap patches. We get a bit of the oval. So there's lots of interesting dynamics that can happen here. One of these, which Toshi will talk about, so I won't linger on it, is comparing this data to already high-resolution, temporal resolution data from all-sky cameras. And you can see that there's stuff going on in the aurora, there's stuff going on in the high temporal resolution supernon data. And now we can actually do better at connecting those two together, which we couldn't do before with the lower resolution supernon data. And this was just a time period where I just looked at all the wide beam data that we had done. I went to the Supermag website and I found an interesting time where it was fairly active during that event. And I just zoomed in on a very thin region. So this is only a few minutes wide. And then, took a look at what was going on there during this active time. And yeah, you can see that, in this particular region here, this flow is enhancing on the order of tens of seconds over this big chunk of space. So we're now capturing that, which we couldn't see before. So one final slide is, I guess I wanted to touch on the implications of this. One of them is, we're getting high time resolution, so we can see high variability things like wave-like activity, ULF waves, Alphen waves, maybe short-lived patches or pulsations. But I also believe it's very important to the study of joule heating and just quantifying the amount of energy coming in, because we know the electric field is highly variable. But when we smooth that out over a longer time integration, we miss a lot of the heating that's actually coming in. So this is kind of something that I whipped up with that interleaving experiment. So this is the lower resolution data on the right, and this is the high time resolution data left, and the high time resolution data on the right. And this isn't quite joule heating because I don't know the conductivity and I don't know the neutral winds, so it's the convection heating per unit conductivity, effectively. But it is a heating rate. It's in watts per meter squared per conductance. And it just goes to show that the amount of heating, that we would miss is quite significant. These things enhance and they move around. Some little patches pop up and then they disappear on the order of seconds. And then, this one down here is just the area integrated version of that heating rate, and the red line is, the high resolution data, and the blue line is the low resolution data. And yeah, we miss all these peaks, and then this is cumulative heating then. And then what we find is when we get to the end of this trace, we actually end up with more joule heating happening overall when we take into account the high resolution data. So this is a fun, why I think this is super relevant and important going forward. So to summarize this, we've been running this for a little while now. You can just go to online, supernon.ca/FBI. FBI stands for the Fast Borealis Ionosphere. There's no law enforcement going to come in here and start deporting me or something like that. We have about 53 days worth of this data so far. That includes the 2024 solar eclipse, though totality doesn't go over the radars. There could be something interesting there. There's too much data to look at right now, so the floor is open if anyone wants to do that. We want people to come to us and say, hey, I've got a satellite flying over in a little bit. Can we make sure that this mode is on? Because right now we're not running this 24/7, because that's a lot of data to run 24/7 and get back from the radars. But we are willing to put this on whenever someone asks for it at the moment. Hankasami, the Hankasami Supernon radar that's just been finished being refurbished and is hoping to go back online later this year, is going to be this Borealis system, so that will just be able to run this mode, and that overlaps nicely with IceCat 3D. And we are working and hoping to do 24/7, 365, but there are technical hurdles with that, not scientific hurdles. So yeah, and I think I'll leave it at that, and I'm sure we're going to talk about all this a lot more for the rest of the session. Thank you.
Thank you, Daniel. So as I mentioned earlier, for those of you who came in late, we have a lot of time for the Q&A, so please feel free to raise your hand, ask questions. We can take multiple questions per speaker.
Thank you. This is very impressive. So you're showing these convection maps you can do on 3.5 seconds. Have you experimented at all with doing them with the Borealis data, but on slightly lower resolution to get better confidence in them? So there would be a significant improvement of things we could be done even with like 15 seconds full. And that would be like 5. So have you played with that at all?
I haven't messed around with the time scales. We've kept it at 3.7 seconds for now, because then it's like apples to apples of, the amount of integration done the old way versus the new way. We do lose some power with doing it how we are doing it with the wide beam, because now instead of sending everything in a narrow direction, we're spreading it out. Spreading it out over the entire field of view. So that does mean a slight loss in data. It amounts to about 10%. So by increasing the integration time, as you described, like we would then regain a little bit of that. So yeah, it would get better.
We have done that through post-processing so far by integrating 3 scans and see how the pattern changes. Essentially doesn't change much. The only difference will be where the power is low, the data becomes noisy, so the confidence level, low power good points will change. But otherwise, seems like 3.7 second data is giving us pretty good accuracy of data. The math, and okay, it's Roger.
Yeah, so first off, congratulations. This is amazing. This is fantastic. When I'm looking at your plots, I see all of this high frequency jiggling, and I'm wondering, have you done an error analysis to figure out how precise your measurements are, and how much of that jiggling is measurement error versus potentially real variability that could even be, Alfvén waves, inductive electric fields at that time scale?
Yeah.
So is that jiggling real or just measurement error?
Yeah, good question. So I haven't done an error analysis. I do have errors. There is errors that come out from this fitting. Some of this is, I don't want to say overfitting, but like the regularization of the fitting isn't changing from fit to fit here, but it might be appropriate to change it, especially if data drops in and out. So because there's no time history in the fitting as well, and you might get occasions where like echoes drop in and out, that would cause a very, very slightly different solution each time, and that contributes to the jiggling. So I have like played with this before, and I used to have like fitting parameters which would like fit to higher orders previously, and that makes the jiggling much worse. So this is actually a lower than I used to use, but it's kind of a balance, because you want to make sure you're resolving all the mesoscale structures that you should be seeing in the data if it's there, but you don't want to like start like overfitting and making it do like weird stuff. So obviously it's still a case-by-case basis where you got to look at the results and make something sensible. For this exact one here that I've shown on the right, I'm pretty confident in that, because those velocity enhancements at least are very sustained. There's probably some error in the actual direction of the vector, but ultimately I think it's minimal.
Yeah, this is great. I agree. Can you go back to where you had the line plot and you had the wide and narrow, and there were images you were there's the heating that you were averaging over. Yeah, that one. At one point in here on the right-hand side, toward the bottom left corner, it gets kind of red or orange, which is not even on the color scale.
I think that's a bug with my Python code, because I made this yesterday.
Okay.
So I think that's because I'm. It's not on the color scale because this is Viridis, and I'm pretty sure there's no red in this. So I think it's just how I've made the GIF, and like how I've tried to. I'm pretty bad at Python, so like I don't think I've managed to make the color look quite right.
Right.
Oh, is it when it loops?
Oh, okay. Let's let it come back around.
We're gonna wait and see.
Yeah.
Oh.
Huh.
Yeah.
It looks kind of persistent.
On my computer, it doesn't look like that.
Oh, wow.
So, yeah. Like if I look at the individual PNG, it doesn't really look like that. So I think that's an artifact of whatever's happening.
Okay. Any other question? If not, Daniel, thank you very much. Okay, the next speaker is Vincent Ledvina. So he would talk about the citizen science aspect of this campaign. So we were able to bring citizen scientists to enhance the scientific output of these campaigns. So Vincent has worked really hard on this, so we invited him to tell us about this coordination effort. Here is a laser pointer.
All right, hello everyone. My name is Vincent Ledvina. I'm a second-year PhD student at the University of Alaska Fairbanks. And I remember back in 2024 at CEDAR, Toshi was talking about this high time resolution mode along with others. And I approached the team and I said, hey, I know a bunch of aurora chasers up in northern Canada who are in the field of view of these radar beams. And they have really high time resolution cameras that they could take all sky images with. And it might be a really good supplement to the radar data that we're getting. So that's what I'm here to talk about today. And this is for a couple periods where we had the high time resolution mode going just this last winter in January and February during moon down. So here's sort of the outline of my presentation. I'll first go into the motivation of why this might be helpful. Then I'll talk about the volunteers that we recruited, the results from this little campaign, lessons learned, and then future plans. And this is just a little sneak peek of the type of data that we were able to get leveraging the aurora chasers. So why did we want to involve aurora chasers? Well, there's really two main points. The first point is that there's increased data availability. So as you all know, Themis ASI is fixed in location. You can't just pick up an observatory and move it somewhere else if it's cloudy. But aurora chasers are mobile. They can set up their cameras where there's clear skies, and if it starts to cloud over, they can move somewhere else. So this really sort of increases the amount of available nights that you have. If there's a really nice event that you see in maybe magnetometer data, but then all the all skies are cloudy, well, talk to an aurora chaser. They probably found a clear slot. And even if the aurora chasers are stationary, more locations, more places that we have all sky camera data means that there's just a higher chance of clear viewing. So for example, in Fairbanks, which is where I live, it's usually really cloudy in town, but Poker Flat is usually clear because it's sort of at a higher elevation, but sometimes it's the opposite. Poker Flat is cloudy and then Fairbanks is clear. So if you just have enough all-sky cameras kind of covering the area, because of how variable the weather is in Fairbanks, you'll get probably one night with clear skies. And then aurora chasers can fill in small observational gaps between the Themis ASI field of views, which I have there at the top. There's not very many, but if you're trying to track a feature that sort of slips between one Themis ASI into the other, but it crosses one of those gaps, it's really nice to have somebody right in that gap so you can track it all the way through. And then the second point, and I think this is really exciting, is that consumer off-the-shelf cameras or COTS cameras have really high spatial and time resolution. Now you can buy a Sony A7S camera on Amazon for $1,000. You can find them used for $600 and produce 10 plus megapixel images every second. And that's really, really powerful. Of course, they're not filtered imagers, so the science that you're doing has to be sort of tailored to the instrument that you have. But if you're trying to look at morphologies or fine scale structures, I really think that citizen scientists can bring a lot to the table in that respect. So who did we contact? I'm an aurora chaser. As some of you may know, I've been into the aurora since I was 16, and I know a lot of people all across Canada and the US, so I just texted a bunch of friends and said, hey, I'm doing this, I'm helping out with this campaign, here are the details, would you like to be a part of it? And I got 6 people to say yes, and they were very excited about it. We prioritized inviting chasers within the super darn radar beams. That's pretty important if we want to do the science comparing the flow patterns and what we're seeing in the all-sky cameras to get people that are actually within the radar beams. And we had some questions, right? Would the volunteer data actually yield new insights compared to what we've been using with Themis ASI, and could we compare the super darn flows with the consumer off-the-shelf cameras? So this was very much just, let's see what happens. No expectations, and I made sure to tell the aurora chasers that as well, if nothing happens, that's still a positive result. We're just happy for you to be involved, and they were super eager about it, and I've been communicating with them throughout the entire process, as we're setting up the campaign and before the campaign starts, making sure that they're all on board. And I think that's really important, is that if you're going to involve aurora chasers or citizen scientists, that you really loop them in to the discussion and make sure that they're feeling included. And so how did the recording data go? Well, we had 3 chasers that recorded data. It ended up being a really cloudy, just couple weeks all across Canada during the periods that we had the high resolution mode going, but we did have 3 aurora chasers record really unique data sets. We had Elisa in Thompson, Manitoba, we had Donna in southern Manitoba, and then we had Drew, who was in Churchill. So Churchill's right along the Hudson Bay, right in a bunch of the super darn beams. And one lesson that we learned, which I'll go over later, is that you should add tracking to your packages if you're trying to ship things across the border from Canada to the US. So I actually don't have Elisa's data yet, and then Donna was able to give me a hard drive when we saw each other at ISSE last month. So Drew luckily has a Starlink, so he was able to dump about 180 gigabytes of raw images that he recorded over 8 nights that we were in this special mode. And then I forwarded those over to the science team after cleaning those up, making sure that the timestamps were correct, making sure that the all-sky images were aligned, so that north is at the top, and all sorts of different things. And then Toshi and others were able to sort of integrate those using SuperDarn and sort of see where Drew's all-sky camera footage could fit in. And so I'm just going to go over a few different events here so that we can see how it worked out. So on the left, you have, and this is for 3 events, so it's the same slide setup, so just remember how this works. On the left, we have Drew's all-sky camera time-lapse. So the exposure is on the bottom left. This was taking an image roughly every, looks like 1.2 seconds. So these cameras can record really, really quick. And I made sure to tell Drew that this is a high time resolution campaign, so we want to get images as quick as possible. And on this night, Drew's movie was able to capture some poleward boundary intensifications, PBIs, and streamers around 4 and 5 UT. And what's really cool is that, if you compare that to the Themis ASI and Rankin Inlet, you can kind of see the equatorward extension of those streamers in the northward part of Drew's video. So it provides added context to what we're seeing in the Themis ASI images. And here's on the right, Drew's all-sky camera field of view, which is in green, overlaid with the other instruments as well as the SuperDarn flow patterns, which is sort of indicated by these rainbow vectors. So this was on January 23rd from around 2 to 6 UT. And then if we go to the next time, this was January 28th around 3 to 5 UT. We had a nice, looks like substorm expansion there around 427, and that was observed by the Gillam Themis ASI, and then the Churchill ASI also captured that, as well as a faint arc poleward of the onset arc, which may be sort of one of these indications of a pre-onset auroral streamer. So, you're also getting really high spatial resolution data here. So each frame is about 12 megapixels. He was using a Sony a7S camera. And what's really cool about this is, you can tell the aurora chaser, you can tell Drew, hey, there's going to be a substorm coming. If that's going to happen, just decrease your shutter speed as much as possible so we can get these really fine scale structures. And so SuperDarn also shows some equatorward flows associated with the streamers, which you can see here. So the next event that was interesting was on February 23rd, over sort of a 5-hour period. Again, Drew's all-sky camera footage is on the left, and then we have, I should start that. We have the SuperDarn measurements overlaid on the right. And the Rankin Inlet Themis all-sky imager observed some repetitive PBIs and streamers, and then Drew's time-lapse from Churchill shows sort of, again, the equatorward extension of that streamer activity. So it's really nice that we have Drew up there recording, because then we can sort of see the context of what we're seeing in the Themis ASIs. I won't let that play too much, just because I want to keep going. So, all this said and done, what were some lessons that we learned? There were definitely some clear wins, but there were also some areas that we could improve for next time. So the clear win is that, the ASI Aurora Chaser footage really complements the Themis ASI observations. And I think that's really cool, because for future campaigns, whether it's our team doing this or any of you, it might help to contact an Aurora Chaser, maybe supply them with an all-sky camera or tell them to take out one of their own cameras and get some really unique footage. Some areas we could improve: we could use more data, we could contact more people, and then we had some Aurora Chasers just recording sort of regular images with their cameras, so just kind of like rectilinear lenses, not ASI lenses. That data is a little harder to work with, so I think in the future, we're going to emphasize that all the aurora chasers switch to an all-sky camera or sort of fisheye lens to get that all-sky camera look. And then, like I was saying before, we had some issues with transferring the files. So just kind of streamlining that process for next time. And we plan on repeating this campaign over the winter. And just some ideas to throw out there, having a wider network of aurora chasers, maybe supplying them with some low-cost imagers, more observing times to hopefully capture clear skies in times with active aurora. So we're planning on having more times where we're running this high-resolution mode. Again, streamline the data upload, and then maybe at some point make everything publicly available on a server, like in real time or quickly after. We're planning on doing that, but just having a more robust sort of file access for the community as well. And so this is a shameless plug, but there is a session at AGU. It's building bridges between the atmosphere, ionosphere, magnetosphere, AIM communities. It's a town hall session. So if you're working on anything MI coupling related, check out the session that we're running at AGU this year. Thank you.
Thank you, Vincent. So when he sent me this PowerPoint file, the file size was 1 gigabyte, the biggest PowerPoint file I've ever seen. It took half an hour for me to download in this conference internet. But it really tells the amount of hard work that Vincent, citizen scientists, put in to make this successful. So thank you, Vincent. Okay, questions? Okay, Christine?
Can you hear me? Sorry.
Okay,
these are
Mia's
terrific
first,
and really
and then
fun to see.
Christine.
But when I was looking at like the January example, I was seeing those beautiful images with all the structure on the left, and I was having a really tough time of connecting the same optical images on the right. Could you walk us through it? And because I just don't see this clear, structure in the middle on the one on the right. It just looks so different.
So maybe Toshi could comment a little bit about that, because I did not integrate the all-sky camera footage into the super darn sort of observations.
The videos play at a different rate, so the different time stamps. So if Vincent, you can stop at the frame on the video on the left and go to the same time on the video on the right, then we will see the same thing.
Let's do that.
So on the left, 431 UT. Yeah, somewhere around there. So we see similar structures. So this tilted auroral forms right around here in my shadow, and that corresponds to this one. Of course, the contrast is different, but it's the same all-sky camera data without any integration.
You're seeing the sort of the current structures. The superdarn is seeing the wrapping around of the auroral regions, which is, I guess, what we've seen in other observations like this. So terrific.
Yeah, so this particular frame is not the best example, but if Vincent can go to another time where, on the video on the right, where we have more superdarn vectors, perhaps at an earlier time. So this event was more for a flow prior to the onset, so this event doesn't have too much flow coverage after the onset, but at some point we see flow enhancements associated with auroral intensifications. And perhaps this video is really not the best, but let's see. If you can go to another event, and then just stop at some point where you see a streamer. So for this event, we had pretty good echo coverage throughout the night. So it's a little faint, but there's an auroral streamer right here. Then there's a flow enhancement right next to it. So that's where you expect an enhanced flow, because that arc is upward current. So we do see the expected electrodynamics behavior in this data, which is cool. These two are two completely independent measurements. Okay, Christine?
Okay. Thanks, Vince. This is a really cool talk and really neat results working with the citizen scientists. I have two questions. One's like a nerdy camera question. The other's a citizen science one. For the cameras, the UTC time would update, I think you said like every 1.2 seconds or something, but then the exposure's at 12 seconds?
Yeah, I actually misspoke. I couldn't see it. It's every 12 seconds on here. Yeah.
Oh, okay.
Yep. Nope.
Okay.
That was just, yeah.
Okay. Then the other question was for like when you're working with citizen scientists, like how do you what's the word? Correctly interact with them respectfully, that they are, because I've heard like some people may think, oh, are we doing work for free? Or so how do you do it like in a respectful manner that is like, oh, we would love to have you work with us, but like not make them feel, I think you see what I'm asking.
Yeah,
like,
no, I definitely get that. I think what worked in this project is that I already had pre-existing connections with a lot of these people. So I know it's a lot of work to say, try and make inroads in these communities to build these relationships, but that would really help ahead of time before reaching out to people, to dialogue with them, especially if they're on social media and they record something really cool. If a scientist comments on one of those images, it just makes their day, and immediately there's a connection there. That's really all it takes. And also, like I included these Aurora chasers as co-authors in the presentation, and I told them I was going to do that. I sent the presentation to them. I had them send me a picture that I could use of them in the field, and sort of made it so that they felt like they were a part of this. So I would just say, treat people with respect. Don't exploit others for their data, and just include them as much as possible.
So toward the end, you mentioned supplying ASIs, or I can't remember how you worded it in the conclusion. But I wondered if you could elaborate on that. Are you providing or offering grants that people could apply for to buy ASIs off the shelf, or are there some that are no longer in use for science but still have some life that you can give them for free? Or so what are some of those options?
Yeah, that's a good question. So we haven't nailed down an exact plan, but I'm also involved with this project called Aurora, which is poster number 83 in the CEDAR section. And I actually brought it with me too, if you saw my poster yesterday. But Jeremy Kazub is the one who manufactures those. And actually, it's just a nice coincidence that a lot of these people that were involved in this campaign are on the list to receive one of these all-sky emitters already. So there's already sort of a plan to get these people, this like super Aurora chaser community, involved with this all-sky camera project. And then the idea is, and since they have this all-sky imager, which kind of uses, again, consumer off-the-shelf technology, but then has a GPS inside, has a magnetometer, has all these different things, it just is really simple then for them to go out and place these down and then record nice images.
I do have a comment, actually. So for Christine's question, there is an easy working group called Arctics, where we publish a handbook. And some of the things we discuss is how to work with citizen scientists. So take a look at that, and if you find something that is not there, we can always add it. And I have also a comment for Vincent and Toshi. This is amazing because this is exactly what we have been talking, organizing a campaign with citizen scientists. So this is something that I feel the community needs to start replicating. So thank you so much.
Yeah, we need people like Vincent who has great connection and working experience with citizen scientists, so that someone can bridge the gap between scientists and citizen scientists. But I think this is a great example. We can take advantage of expertise like what Vincent has to do more than just super run, but more sky cameras, to GPS, magnetometers. There are a lot of potential out there, I think. All right, anybody else? All right, thank you, Vincent.
Can I ask a quick question from online?
Was there a question online?
Yeah, please.
Yeah, so just very quickly, I'm familiar with the Aurorasaurus blog, but I'm wondering, is there some more rapid mechanism for citizen scientists to communicate with each other and working scientists? For example, to indicate that there's a storm or a substorm, or indicate that they've seen some unique structure?
Yeah, that's a good question. To my knowledge, it's mainly done through just like social media, just through, yeah, just like Twitter and Facebook and Instagram and things like that. Aurora Source also does have an ambassador network, so if you're a scientist and you want to start forming some connections with citizen scientists, I recommend that you just email, I think it's aurorasource.info@gmail.com. Usually these ambassadors are scientists in our field that come and give presentations and then ask the community if they can help provide observations. So that's one way that you could maybe build a connection. But in terms of rapid response, it just is, I think, mostly done through social media at this point.
Skyward then.
All right. Very nice. Yeah, thank you for the talk.
All right, so I'd like to give a brief report about a few science cases that we can do based on this campaign data. Taking advantage of this workshop spirit, I'd like to dive into my backup slides to answer Roger's question about what this wobble is in the convection map. So some of them are noise, but others are real. So here's a real example, which is ULF wave situation. So we have a flow vortex in here, and that is moving over time at a very short time scale. We were barely resolving them in the 1 minute cadence of data that were available in the past. This is the same time time frame of data, but at 3.7 second cadence. So what we see is a very clear forward motion of the fast flow channels, and pretty repetitive, and they correlate very well with the ground magnetic field oscillation. So it's a real flow oscillation. And what we can see here is it looks like just one flow channel in 1 minute data, but in high time resolution data, it's actually 2 flow channels combined. And for the third one, it's more crazy. It looks like one channel again, but it has one enhanced flow in the polar portion and 2 separate things in the equatorial portion. And we really couldn't see them before. And by staring at the ground magnetometer data, there's a little bit of kink in this oscillation in the magnetic field. It's really not pure sinusoidal way, but multi-frequency of ULF oscillations are combined. So those kind of things are now being resolved in high time resolution data. So that's part of the oscillation in the vortices we are seeing. Okay, so this is similar to what Daniel has shown in his presentation, but the previously what we were able to do was to get the 2 minute resolution of convection map like this. So under southward IMF, as expected, we see 2-cell convection. It doesn't change too much, so that's nice. But now we have the high time resolution measurements over North America in this highlighted region. So then by looking at the convection in that area at the high time resolution, we see a lot more structures in there. So we see westward flow over here, and equatorial flows over there, the magnetic midnight down there, the dusk is to the left. And then what we see here is a dusk side convection cell, but this one is changing at very short time scale. Some of the flows are moving up and down. So that's based on what we see in the line of sight measurements in the previous slide. So this is real flow structure changing at the ULF frequency. And some of them are correlated with the auroral structure right here. Flow channels are nicely aligned with the fast flow. So there's a flow shear at the location of the auroral arc. So that's exactly what we expect when we have the auroral arc, where we have the converging electric field. So that the level of details now we can resolve, but couldn't be done before. So that's really exciting opportunity to do things like flow channel evolution, flow shears, flow vortices, and ULF and whatnot. Okay, so with those, so I'd like to talk about a few science examples, and of course we can do more. So here is a substorm pre-onset flow situation. So what we knew before from all-sky camera measurements were that prior to a substorm auroral breakup, we have an auroral intensification near the polar boundary of the auroral oval. This corresponds to the magnetotail connection. And then, so there will be a fast earthward flow. So the ionospheric signature is an equatorward flow, or the equatorward extending auroral arc called a streamer. Back then, we didn't have any event with great flow measurements. So we were just speculating what flows were doing. And then by using Bill Bristol's technique with 2-minute resolution convection maps, we were able to see that there are indeed fast flows prior to substorm onset. So substorm onset took place over here. So 2 minutes before, there was an indication that there was a plasma flow going toward an auroral arc. So if this is true, this does indicate the plasma transport, change in pressure gradient in the magnetotail that sets off the substorm onset. But the problem was that this flow comes and goes in a very short time scale. So there was only one scan of super-run data that was showing. So we're not really confident this was even a flow channel. There may be just a beam that happened to scan the wide flow structure. So Christine Gabriel's, Bear Gerdel Court have also done statistical studies about flow channels. But oftentimes the flows are coming and going at very short time scales. So although we were able to characterize flow structures fairly well, so we were still thinking that we were missing the fundamental features of plasma flows. So now we have high time resolution measurements. So let's take a look. So the background is Temesov-sky camera data, and now we see fast flows coming down. So going back, initial flows are weak, and then flows starts to intensify in the middle. There was no response in the aurora yet, so it's clearly showing that the flows are coming first. Flows are intensifying, and then the substorm onset took place. The flows intensified, and then substorm onset right here. So now the causality is very clear. The plasma flow is transporting the plasma in the magnetotail, changing pressure structures, and that is followed by substorm onset. So this clearly provide the time sequence of events that we're speculating. Now we have the citizen scientist contribution, like what Vincent has shown in the previous talk. So in all-sky camera, in the previous video, actually it's not quite clear what's going on during the flow enhancement prior to the onset. And that was probably because it's white light camera and also at low elevation, so we couldn't really see what was going on. So this red circle is the data from the citizen scientist. So that this person sitting right between these two white light all-sky cameras, so it nicely fills the gap. So substorm onset is very clearly seen, and it's very faint, but prior to the onset, there are faint auroral structures right forward of onset around here, and that corresponds to fast flows going on over here. And I'll show you the kilogram in the next slide. So these coordinated measurements by citizen scientists and super-run provided a great picture about what's going on. So here's a kilogram in case the video was a bit hard to see. So the red line in the first panel shows the southward IMF. So it's a very textbook substorm event. So it set off the growth phase. So soon after that, the second panel is a 2-minute version of the equatorial plasma flow from the spherical harmonic feeding. So we do see enhanced flow due to southward IMF. It looks very smooth, not much time evolution. The third panel shows us equatorward flow that in the high time resolution data. So we see overall similar flow enhancement, but we see a lot more structures inside, and there is clearly a flow enhancement prior to substorm onset, and also the equatorial progression of these flow structures. So that was really not visible in the previous version of the data. And this equatorial progression nicely corresponds to an intensification of the aurora prior to substorm onset, which we call auroral streamer. So we were guessing the flow structures based on these optical measurements, but now we have the similar cadence of flow data that justify that this kind of plasma transport that really exists. So that's very remarkable. So very quickly, I'd like to jump in another event. This is a steady southward IMF event. The red line shows the IMF BZ, prolonged southward IMF. So in this event, so there was a great amount of echo near midnight, which is this blue line. The polar boundary of the auroral oval is here. So there are multiple intensifications showing multiple tail reconnections. And associated with them, there are auroral structures extending down to this green circle, which is, again, the citizen scientist's all-sky camera data. So now the aurora is still up here, but later on, we see that these auroral intensifications extend down here. And for each one of them, we see flow enhancements. Sometimes flows are there even if the aurora is very weak. So this high-time resolution superrun data is very sensitive to the small-scale modulation of plasma flows. So toward the end of this video, there are some good instances where there are strong aurora, like here. The moderate auroral intensification, and there was a flow enhancement right next to it. So that really makes sense from the physics standpoint. Okay, in the kilogram format, we see the similar story, multiple auroral intensifications. We're in quite steady southward IMF. In spherical harmonic fitting, we don't really resolve this kind of short time scale flows. We usually get just some variations of background flows, but they don't really correlate with the aurora very well. So that was a problem in the past. But now we see very short time scale burst of plasma flows that comes with auroral intensifications. This is a north-south component, it's an east-west component. There is a very clear shear in the plasma flow across the open-closed boundary. So that, again, indicates a strong converging electric field that is associated with the auroral intensification. So in summary, so now we have really great advance in the capability of knowing what the convection is doing at the comparable time scale to the auroral imaging. So now we can resolve flow channels, ULF, and fast variation of convection, including their structures. So that opens up many pathways forward for doing science. So that's really great. And again, so the citizen science contribution is very critical, so we do need to expand that. And also, we will make this convection data available to everyone. So not only things that we just talked about, there are many things we can do, day-side convection, polar cap convection, etc. So we as a community can work together to utilize these and encourage the radar community to expand this capability so that we can eventually extend this to the global scale size. That's it. Thank you. Okay, Christine.
Sorry, my question is actually because I missed the beginning of Dan's talk earlier. Is the SuperDARN, are all of them in the high latitude region having that fanned 3.5 second cadence that are feeding into your maps? Or is it just like a few of them?
So for now, only the Canadian SuperDARN radars are doing this. So this is Dan's first slide. So only these red highlighted radars operate at 3.8 second cadence, and other radars still doing 1 or 2 minute scans. So in my video, I stitched those two different time resolution data together. So within this area, the convection maps updated every 3.7 seconds, but while other regions, the convection is evolving at 2 minutes. So there are still limitations. We can only do this kind of science in this area, so that's why it only highlights true convection at this point. But we'll come to what US radars are going to do. That's the point of Bill's presentation right after me. So do see what the US radar PIs are thinking at this point.
Cool. Thank you.
All right, if not, we'll move on to Bill Bristol's presentation.
sorry, Toshi. Can I ask one quick question about the PC5 pulsations?
Jason, can you repeat your question?
Yeah, can I ask just a question about the PC5 pulsations? Have you looked at any, possible conjugate satellite data that might indicate like magnetopause cavity modes or something like that? Or have you seen like solar wind dynamic pressure oscillations or something that is typically associated with the PC5 pulsations?
Yeah, that's the kind of thing that we do need to do from now on. So in this session, we are reporting the kind of first light of the campaign measurement that was done just a few months ago. So we need more people to jump in and look at data and take advantage of high-resolution measurements in the ionosphere and understand what's going on in the MI coupling system. So yeah, what you said is what we really need to do.
All right, yeah, thank you so much.
Okay, so now, like what Christine asked, we should wonder about what's the future of the radar operations. So the U.S. radar PAs have been working hard on upgrading other radars. So we asked Bill Bristow to talk about the current status and future plans for the U.S. and Iceland radars.
Okay, so how come everyone keeps asking me Christine's question? Larry and Toshi were at the SuperDarn meeting, and Toshi asked me to give this talk. They also cornered me and got a commitment that we would get this capability on the U.S. radars. So we actually are making progress towards being able to do this. So this is a discussion of that. So we actually had this capability a few years back. This is some plots from 2008 when we first started doing the multi-receiver, multi-synthesizer observations. And we developed the capability to arbitrarily choose our beam width at that time. It was just the main observations that we used this were for observations of the HARP-heated region. We could image the HARP region instantaneously, essentially. We actually, you can go down to 1 second cadence if you have a big target to look at. So the answer, can the U.S. radars do this? Well, yeah, we can. We have the hardware. We also are kind of in our third iteration of software for this, and didn't maintain that capability in the latest incarnation. The thing that we did push on in our data was mostly spatial resolution. So this is work from, I think I had it on the previous thesis. I don't know if folks, some folks know Todd Paris. Todd Paris was a student of mine back in 2000s. Todd is now at AFRL. I don't know, he's moved up to some level now. But some of you, if you've worked with AFRL, probably know Todd, and maybe some remember him from when he was a student. Great engineer, did most of this work back then. And this is some of his work where we were looking at the HARP-heated volume. And if you look at that, the spatial resolution is phenomenal in the angular dimension. He's using maximum entropy spectra to get the angular measurement out of this. So that's the main thing we focused on is getting the spatial resolution out of the measurements. But this is simultaneously doing broad beam and the high spatial resolution observation or analysis. And this is where we are now with the current system. This is 2018, I think. Yeah. So this is looking at the data using the multi-receiver data to do radar imaging, so we can image in velocity and have. Well, this is done at a 1 degree angular resolution and 15 kilometer range resolution. So that's our main capability right now in that regard. Okay, but that was just the Kodiak radar, and we have the same hardware installed at King Salmon, Kodiak, and in our two Antarctic radars at McMurdo and South Pole. Last year, I guess, before the eclipse, Mike was able to secure funding to upgrade the Blackstone radar so that it could get observations during the eclipse. They took our system and installed it at Blackstone. So this is the crew at VT during the installation of the hardware. So they have it in there. They are getting great observations. This is from the eclipse using the USRP multi-receiver synthesizer data. Mike can tell you more about that. Okay, now also, Iceland, I think this morning, Bruce Fritz mentioned that ONR funded a DURUP to Dartmouth. So Simon and Evan have been doing the same thing. They have purchased all the hardware for both the Iceland and the Oregon systems. They went up just after the semester was over and put in the instruments or the electronics in at Iceland. So this is in their lab at Dartmouth, getting all this stuff together. A couple of undergraduates did most of the work for putting things together there. And then they made the trip up to Iceland and have it all installed. So Iceland is a dual radar system. So we've got fields of view that are pointing, east and west. And so there's a bit more hardware there than there is at our single radar sites. In addition, there's significant additional software complications to run two radars at the same site. And that's where we've been, for the last few months, concentrating our development, is just making it possible to run the USRP system on two radars that are at the same site. So that software is there now, and they're running on. They're only running on half of it right now. They're only using Iceland West, so this is observations where they're looking at two different frequencies at the same time. Simon has a problem with the heat in the building, so he's going up soon to put in extra ventilation, and then they'll be able to turn on the east field of view, and we'll have the two radars there. So now that means Iceland and the Alaska radars, so that the radars that are adjacent to the Canadian radars will have this capability. So they all have the USRP systems, and it's just a matter at this point of re-implementing the software. The electronics will be in at Christmas Valley later this summer, so we'll have it starting in two of the mid-latitude sites. VT is looking for funding to complete their systems. So Hays, Kansas, in the middle of the country, and then Goose Bay and Kapuskasing both need the money to buy the electronics. And I need to get back to my office and start writing code so that we can get this on the radars. So that's the status.
Questions to Bill? Yes, Dan?
Yeah, thanks. Yeah, congratulations for doing it 20 years ago. Yeah, I think the imaging stuff is like really great, and it's like, it is the real future to do proper imaging. I had a question, unless anyone wants to ask something first, about the original work you showed by Todd Paris with the HARP data. It kind of looked like, I wonder if it's like this one.
Yep.
It kind of looks like it's smeared across all the azimuth, like that HARP intensification, like right in the middle. It almost looks like it's showing up in every single beam, so to speak.
Okay, so even when you're doing, so he's using, I think, music to do his spectral analysis in the azimuthal direction. So any spectral estimator has side lobes. Even music has some, and so there is some smearing there. You've got such a big target right in the middle. So yeah, it's going to have that. We could probably, if you're doing a different estimation technique, you could probably get better localization.
Yeah. Well, with the more recent stuff, at least, I really think that's the way to go forward, because you can do everything at the same time, and then you can also do the pulse encoding, and you just get way better SNR.
Yep.
And you have your cake and eat it too, basically, at that point.
Yeah, I mean, this was coded pulses, but yeah, then music in the azimuth.
Yue, in the back. Oh, Bear is bringing a microphone from behind you.
The high resolution and high cadence superdown observation definitely is super important. Really appreciate. I wonder if the funding is limited, which one will be more feasible, get high spatial resolution or high cadence?
So luckily, my time is worthless. So at this point, it's just writing code, and we will be able to do both simultaneously.
How often can you run your Alaska and Iceland radars at high time resolution mode?
So we continuously, save all of the antenna data, individual antenna data. So the only downside of doing it for us, it doesn't increase our volume of saved data. It's just the decrease of SNR. So once we implement it, see if it is a significant hit, then we will decide if we do it regularly or not.
Okay, so
don't you guys save your raw data, Dan? Yeah. You do. So it's just the analyzed data that's bigger.
Right. It's getting it back from the radars as well.
Oh,
is like tricky, because then we can produce like a downsampled data product to like save on space, and then go back and reprocess if we need to. But we haven't got the software pipeline up to do it automatically.
So we bring ours via SneakerNet. You just have disks at the site, and people bring them home or send them to me. So.
Then when the Canadian radars are going to do the high resolution campaign again, are you able to coordinate so that you can run at the same time?
Maybe, if I get it done.
Yeah, that would be a great step forward to increase the coverage, to get down to convection at larger scale, sometimes suborbital convection that we can't see in Canadian radars. So yeah, with more radars we can do new science. Okay, this is also a good time for people who don't do this kind of flow to radar science to provide input to the radar PIs. Micronomy is also the PI sitting there. So if any comments, input, questions, this is a perfect time to make. Okay, or Mike, do you have anything to add to Bill's presentation regarding status and future of the U.S. radars?
Bill covered it pretty well. Yeah, we are doing what we can to convert our radars to the USRP-based electronics. We had a success there with Blackstone, and in principle can join the party here of doing the high-resolution stuff. It's still early days for it. We're working through some software issues, and there's stuff we need to do with Bill. And the other radars, as Bill said, we're looking for funding to do those conversions.
Can I ask a question? Because
Yeah,
I got lost. Bill, is the high resolution also about 3 seconds, similar to what Dan, 3.5 seconds? It will be. Okay, thank you.
You analyze it in 3 seconds now. It's just you don't have the broad transmit beam. But that will be implemented as soon as I can get it done.
Okay, thank you.
Okay, if no one else, okay, thank you, Bill. Okay, so now we move on to contributor presentations. And again, we have ample time to ask questions. So we'll continue to operate at the workshop mode. All right, so here's the laser point. So Moines will tell us about the electrojet turbulence, recent progress in understanding the Faraday-Booneman instability.
So returning once again to my thesis project of so long ago, but we're making really good progress. You can't possibly understand what this movie is showing you yet, but I'm hoping by the end of the 7 minutes, we'll get there. So let me give a little context. We're talking about electrojet instabilities in the E-region ionosphere. So we're talking about a region between 90 and 140 kilometers. This is the highly collisional regime, partially ionized, tends to have very strong electric fields in the auroral zone coming down from above and creates turbulence in this region as the currents get driven through the lower ionosphere. There are plasma waves that develop. These were some of the first radar echoes were detected from this region. They were labeled very creatively types 1 through 4 in the 1940s, I believe. And we've also explored this extensively with rockets. There are big radars all over the planet that see these things. You also get this kind of wave structure at Hikamarka on the equator. We're not going to talk about that. But we're primarily going to focus on Farley-Booneman waves and also thermally modified Farley-Booneman waves, and the other kinds of waves that occur in this region we'll ignore at the moment. They're important because, well, I hope they're important because I've worked on them so long. That's why I hope they're important. But anyway, they're also important because as you drive immense currents through the lower ionosphere, that ionosphere becomes turbulent. It raises the temperature of the plasma, and which affects the recombination, increases the plasma density, and therefore reduces the conductivity. Also, the turbulence itself can cause anomalous conductivity and therefore modify how much current the whole system can carry. So, and also they're important because we use them as diagnostics, and some of these SuperDARN measurements do actually come from the E-region, although I think my understanding is it's a minority of the measurements. So here's an example of where we see optical measurements really zoomed in with these Farley-Booneman waves. The optical measurements are the green images, and you can see there are these echoes that come back from the E-region ionosphere measured by the Ice Bear radar. These are from Magnus Iverson's recent paper. And you can see, I guess this is a laser point, never mind. You can see that the turbulence sort of wraps itself around the auroral region. We think we understand that to some degree. Where the aurora is, you suppress the wave generation. Also, the strongest electric fields tend to be on the edge of where there is precipitation. Okay, so I've been simulating these for 30 years now. And these are sort of the kinds of simulations we could do about 15 years ago. And you see, what you're seeing is plasma density. It's in a box perpendicular to the magnetic field, so the magnetic field goes into the board. You see high density and low density represented by different colors. You have the direction, the current flows is the E0 direction. That's the direction that the system wants to use to close the whole magnetosphere, ionosphere, thermosphere current system. And of course, at the same time, you get E cross B drifting perpendicular, and the waves predominantly go in the E cross B drifting system. Okay, so, and from this, we've sort of explored the physics and built models that tell us about the anomalous conductivity in the system. So if you plot altitude on the bottom, I know that's sort of turned around. We usually have altitude going up, but it's the independent variable here, versus conductivity on the left axis. Using a somewhat heuristic model, you can sort of see that we predict that you're going to get the bottom line shows the conductivity you would get without turbulence, and then the middle line shows if you get conductivity that's enhanced by nonlinear transport. This is an instantaneous, what's called, it's nonlinear or perturbed plasma transport across magnetic field lines, because electrons try to get across the field lines, but they're basically magnetized and stuck, and the turbulence actually enhances that. And then Lastly, the enhanced conductivity you get by raising the temperature of the whole system and therefore changing the plasma density, but although that takes about 10 minutes to come into effect. And we just predict that there's going to be some substantial effect where you get this turbulence. In fact, factors of 2 or 4 in the conductivity, which hopefully matters to the system. What's new here is we now, supercomputers have gotten extremely powerful. We can do simulations with 30,000+ cores simultaneously, and that is what you're looking at, is a simulation with 30,000+ cores, where the bottom of the system is the bottom of the auroral region, extending up 32,000 grid cells to where the conductivities, or I should say the collision rates, are enormously high because there's a ton of neutral collisions in the bottom, to the top where the collision rates are very, very low. And you can see the Farley-Buneman system. And then this is a 3D simulation. It's just a cut. It's very tricky to simulate, to show 3D systems. So this is just a cut through the system. And it goes in, both in the E cross B direction, which is what you see, and then there's another plane which is in the E0 direction, which you don't see in this picture. And so that's what you're looking at. The magnetic field is strictly vertical, so we're mimicking a little tube along the magnetic field. You might call it a flux tube, although in the low-air ionosphere we rarely think of them as flux tubes because ions and electrons are somewhat disconnected. But what's new here is we've always treated each altitude independently. We've only been able to study one altitude at a time, one collision rate at a time, a little tiny piece of this. But what you can see is that the waves throughout the system, as you propagate up and down, are very much connected to each other. And that's because, these waves, these density perturbations, which is what you're looking at, are associated with electric field perturbations. Those electric field perturbations have to travel up and down B very efficiently. You can't turn the electric field off locally. And so they're talking to each other up and down. So the whole system is connected. And the question is, what is the impact of that? We've never really been able to explore it. It's a tricky thing to explore even analytically. But now we have this tool that can help us explore it both analytically. Let me show you let me see if I can get this working properly. What you're looking at now is just 8 cuts in the other direction, right? So there's all these altitudes, and I basically picked 8 altitudes, and you can see all the waves. And you can see the waves change as a function of altitude, although they do talk to each other. Here, I can get this going at the same time. They do talk to each other, but they also are different wavelengths. They are, you can see it's longer wavelengths at the top, shorter wavelengths actually at the bottom. In the middle, you get a more turbulent field. It's more connected. So using the information from the simulations, combining that with theory, presumably we can actually now do an even better job of getting what the anomalous conductivities are, what the anomalous heating is. And also, this is a diagnostic tool, right? Because we get plasma density irregularities that scatter radio waves, and the scattered radio waves that give us a diagnostic tool. Presumably, it also would have an impact on HF propagation and all that. And now we can really explore it in full 3D in a way we've never been able to do it before. So that's my story. So we have new simulation capability, which will hopefully allow us to really better understand what exactly it is nature is doing in the auroral ionosphere when you drive storms and substorm currents through the electrojet. Thank you.
Hi, Mears. This is Phil. Congratulations. That's hard to believe you could do the whole stack. I am sure that you and Yakov have already started thinking about what you thought you knew before that was wrong when you've got the entire altitude stack. Is there anything you can say, even in a preliminary sense, about what seems to be emerging from that?
Well, to be honest, these are only about 3 weeks old.
Oh, come on, but you must be able to say something.
But, I mean, it's a question of, what is the relative effect of connection up and down B
Yes.
to the local? And we have to, it has to be done quantitatively. So we're going to have to do a comparison. And we don't have any conclusions yet. We really haven't made the quantitative comparison that needs to be done. We need to do, for each of those altitudes, we need to do an isolated simulation and the theory, and then compare it to the full simulation and say, how does it change the picture? How does it change the dominant wavelength? How does it change the anomalous transport? How does it change the heating effects? I can't say that we know. There are various parameters in Yakov's hand-waving sort of theory of the anomalous conductivity, and that, we can sort of say, okay, we got that a little wrong or right, but we don't know the answer yet, so it's too new.
I will just say, just visually from the back of the room, it's quite clear that, just looking at the connected waves, the wavelength is changing quite dramatically as you're going up in altitude from that vertical slice that you have.
Yeah, the waves start up at about 2 meters when they start, but then when they're turbulent, they sort of seem to settle into more like 5 to 10 meter structures, although I haven't run it long enough because this run used up 15% of my 3-year allocation on the supercomputer. So I can't do a lot of runs until I'm sure it's perfect. Then I can do a handful of comparison runs. So,
great.
Yeah, these are big.
Roger.
Yeah, thanks for sharing this. This is fantastic. In terms of which parameters you're varying in the vertical column, so obviously collision frequency changes as a function of height. But it looks to me like the wave phase velocity is faster at the top than at the bottom. So is the initial temperature profile uniform, or is there a temperature gradient as well?
Yeah, this simulation, well, it's my biggest simulation. I messed up with a parameter at the top, and I'm getting anomalous heating up there. So so I've spent the last 3 weeks fixing, who has a poster this afternoon, and I have spent the last 3 weeks figuring out how to fix that anomalous heating. It really is just fluctuation dissipation heating when you have very little, I'm getting into the nitty gritty, but you have very few particles per cell. You get a high level of fluctuation dissipation when there's low collisionality. The high collisionality sort of means it runs into things and it holds that in check, and so the temperatures don't get very high. There's a big question. The electrons have very rapid along B transport, right? So if they get hot down here, it doesn't take them long to get up here, 10 kilometers up, right? If they're going 40 kilometers a second. So just from thermal speed, right?
Yeah, they should have an extremely efficient thermal conductivity along B.
Yeah, in the top region where the collisions are low. In the bottom region, it all gets stuck.
But in terms of the initial profile, is it a uniform density profile, or is there a density gradient with altitude?
So the plasma density, the 0th order, we kept it just uniform density, uniform initial electric field. There'll be an anomalous electric field which will modify that, but which we'll look at. We tried to have as few sort of arbitrary variables, so the only really arbitrary thing that's changing as a function of altitude is the collision rate.
Yeah.
Now that means that you have an ambient 0th order temperature of the plasma will be different at the top versus the bottom because that collision rate does determine that. So we let that set itself just through the natural physics, the 0th order physics of what the thermal, and we have a fluid equation, but this is a fully kinetic code. This is all PIC. So we have a fluid equation to see if we're anywhere near reality, and actually it's really quite good, except we also get an enhanced fluctuation dissipation level of heating because we only have a handful of particles per cell. And so, but we do a lot of filtering and we play games to make sure we stay close to what the fluid equations predict.
Yeah, extremely interesting. Thanks.
Get into the nuts and bolts, which is essential.
Anyone else?
So I have a question, if no one else in the room does.
Sure, go ahead.
So I was wondering if you could elaborate again on the relationship between the turbulence, which seems to be showing up around the optical emissions. I mean, is this just conductance enhanced by precipitation shorting out localized electric fields, or what's the deal there?
Yeah, so you're referring to essentially this image.
Yeah, exactly. Yep.
Right. That to zeroth order, that's correct. We put out a paper Yakov Demont put out a first author paper where he showed that to zeroth order, yes, you get a lot of heating. Heating causes a high diffusivity. Diffusion wipes out wave growth. And it's even worse than that because the collision rates are a function of velocity. So when things get really hot, there's an even faster elimination of the waves. But yeah, I think that's the best understanding is basically the heating. The electric fields are also strongest around the precipitation patches typically. That's the model as well. So you have higher electric fields, which drives wave growth. And also, of course, that's where the current flows in the high. And the hotter regions where the precipitation occur really does suppress the instability as well. But it's really interesting that you can see this wrapping phenomena quite frequently when, you sort of have to get everything lined up right. The cameras have to have the right angle as well as the radar. But
yeah, it's really nice. Yeah, thank you for your talk.
I recommend the Magnus Iverson paper of 2024. It's a terrific exploration of this, and he also does it in conjunction with satellites going over.
Iverson 2024, check it out. Okay, thank you.
All right, thank you, Mies. All right, next speaker is Yang Shen.
All right. Hello, everyone. My name is Yang Shen from UCLA. I'm going to talk about one of the future science applications using high-resolution super-Down convection map along with another 3-second data set. It's a real redline auroral imagers. So I'm going to show some examples of what can we do using together the redline auroral imager with the super-Down convection map. We can study some features that we have not seen before and to a great extent. So I'll just start here. I'm going to talk about the low-energy redline auroral streamers and their potential linkage to the wave-particle interactions in the magnetosphere involving time domain structures, or TDS. So previous study from Sergey et al. Have shown that there were two types of particle precipitation associated with auroral streamers. So the first type is from quasi-electrostatic coupling, where electrons are accelerated by parallel electrical fields leading to discrete auroras. And so here is a very well-known diagram showing that the auroral streamers sits near the westward side of a wider flow channel, right in the narrow upward field line current region. And the second type is from wave-driven coupling. So essentially, the auroral streamers is a type of a diffuse auroral precipitation from wave-particle interactions. So the waves cause pitch angle scattering of plasma sheet electrons. So here in this example, the DMSP satellite first traversed an emerging auroral streamer structures at the high latitude region with a discrete auroral signature. And then the DMSP continued equatorward, passing through another auroral streamer structures as well-developed structure and dominated by diffuse auroral precipitation. As you can see, this plasma sheet type of precipitation without significant electron acceleration. So there's also previous studies show that auroral streamers exhibit different features when you look at it in different imagers. Most of the studies use imagers sensitive to larger than 1 keV electron precipitation. So for example, from the green line or imager, white line, all sky camera, and the UV imagers. But some of the auroral streamers, they are associated with low energy, less than 1 keV electron precipitation, better captured by red line auroral imagers. So here I'm showing one example from Capco et al. So where they see a pre-onset auroral streamer in the green line, which is located exactly at the westward edge of a red diffuse auroral patch. And this red line streamer-like structures was associated with a plasma sheet flow burst. They have a conjunction observation in the magnetosphere, and they hypothesized that this red line auroral patch was driven by pitch angle scattering of cold plasma sheet electrons. So I'm going to show some observations supporting the idea of red line auroral streamers from wave-particle interactions. So this is our observation. We have a conjunction between CMS and Regal auroral imager, along with other different kind of auroral imagers on the ground. So this is an observation from the magnetosphere, the panels from top to bottom. So here you see fast line flows in the magnetosphere. Focus on this part. The earthward line flow velocity exceeding, getting closer to 100 kilometers per second was associated with an electron injection indicated by the time, the time indicated by the vertical dash line, and they were associated with broadband electrostatic fluctuations indicative of time domain structures. So this is shown in the third panel. This is the electrical field spectrogram. There were also relatively weak electron cyclotron harmonic waves or ECH waves. So these two types of waves are known to drive diffuse auroral precipitation. And based on these observations, along with quasi-linear diffusion theory, we can estimate the precipitating distributions from these observations. And this is shown as the second to the bottom panel. We can also calculate the integral precipitating energy flux for individual wave mode. So this is plotted in the bottom panel. We see that in this case, TDS-driven precipitation clearly dominates. And this little red bar identified the time interval when we have conjunctions with ground-based auroral observations. So this is conjugate auroral observations observed around the time of injection and ion flows, so which is indicated by the vertical blue dash line. And looking at the ASI auroral kilogram, is a white line auroral observation. We see that it's a primary diffuse auroras located poleward of the black auroral and auroral torch. But if you look at the red line auroral emission from Regal and MSP data, you see very structured streamer-like filaments moving equatorward and eastward, also poleward of the black auroral and auroral torch. And using MSP green to red auroral emission intensity ratios, we could estimate the precipitating energies of these streamer-like structures, and it turns out to be very low energy, 0.2 to 0.5 keV. And when we look at the conjugate CMS estimated precipitating distributions, we can get the characteristic energy and compare it. The resulting characteristic energy is also 0.3 keV, fairly consistent observations. And these two figures show the example red line streamer-like structures clearly visible in the red line Regal data, barely detectable, embedded in the diffuse background in the white line images. I also show the corresponding magnetic footprint of Siemens spacecraft in the Regal data in comparison with the Signal model predictions. So how do we estimate the footprint? Well, we examined the cross correlation between CMES estimated precipitating energy flux with auroral brightness for both Regal and ASI for all the 2D pixels. So here I'm showing this correlation map from Regal as a function of geographic latitude and longitude. You could see a very tiny region with very high correlation up to 0.9. And this is the region where we think this is the most likely CMES footprint. It's about a degree in latitude away from the second angle model predictions. So the figure on the right, the top panel, shows the corresponding measurement of red line auroral intensity variations, showing the black line with correlated CMES predicted energy fluxes driven by the diffuse auroral due to TDS. We see highly correlated data set. While correlation doesn't mean causation, we use auroral transport code, T-Rex ATM from Jun Liang from University of Calgary, and we can directly compare the forward simulated auroral intensity with observations. This is shown in the second panel here. The model is in magenta line, the black line is observation. So from this comparison, we conclude that the TDS-driven diffuse precipitation can well explain the red line low energy auroral streamer structure. And so in addition to Silverdown convection map and all sky imagers, Regal red line data could be also useful to study low energy auroral streamers and magnetosphere night side transition region dynamics. I'll stop here and take questions if you have.
Thanks for the really interesting talk. I think it's because I'm tired, but can you explain the plot where you're comparing the T-Rex ATM forward modeled red line and the data? Because on the y-axis I see Rayleigh's, but on the top I see TDS-driven precipitated energy flux. So what is the data that you're comparing with the ATM model? Is it energy flux or is it the brightness in Rayleigh?
Yeah, so this top panel, we indeed were plotting the precipitating energy flux in comparison with the Rayleigh auroral intensity. So this is the data we used to identify the highest correlation region. But later, when we identify this highest correlation region, we use this precipitation data as input into the T-Rex ATM model. And this is plotted as a Rayleigh auroral intensity. So we are comparing apple with apple. So this bottom panel are all Rayleigh data. The magenta line is the T-Rex ATM model output. And the black line is the observed auroral red line intensity variations at that point.
Okay.
But you can get the model emission if you wish, I believe, with a Jun Liang's model. So you're comparing the measured luminosity and energy flux, but can you get the emission from the model?
Yes, we can.
In that case, you can compare apple and apple.
Yes, so this is showing this panel. So I'm sorry I didn't make it clear. This one, we're comparing the forward simulated auroral intensity with observed auroral intensity.
Does that make sense, Christine? So he has the energy flux. So he has wave measurements. So he put that into the model, and then drive precipitation. So that's the red axis in the top panel. And that appears to correlate with auroral intensity fairly well. So auroral intensity is a measured auroral intensity. And then he used Julian's model to get the red line emission out of this precipitation, and that's the bottom panel with the two different types of precipitation or wave modes. And then, the values are somewhat different depending on what you put in, but at least the correlation is there. So the idea is that this precipitation is responsible for this red line streamer.
Okay, yeah, I think I'm following now. The top one is two different data.
Two different quantities.
One is one is the intensity, one is the energy flux, and then you use the energy flux as input to the model to get out the intensity for the bottom plot.
Right, I was actually using, to be more precise, I'm using 4 precipitating distributions estimated from CIMEX as input to get out auroral intensities from Gene's model.
All right, Yang, thank you very much.
Thank you.
Do we have time for one very naive question about that talk?
Okay, Jason, go ahead.
I guess I'm just wondering, what do you think explains which streamers develop the FAPDs and monoenergetic precipitation versus the ones that just show diffuse?
So in this example, we are considering primarily the diffuse auroral precipitation, not those monoenergetic discrete auroras. And so this correlation doesn't mean that diffuse auroral diffuse precipitation explains all the auroral features we observed. There is 2 bumps, as you see in the data, and we think that 2 enhancement of red line streamer auroral intensity is the TDS-driven precipitation can well explain that. Do you think?
Thank you.
Yeah. Okay. Cool.
All right, thank you again. All right, so the next speaker is ULN about the interhemispheric asymmetry in the MIT coupling system for the solar eclipse. Okay, here is the
All right. First, I heard the high-resolution superdown convection patterns have been mentioned in several previous talks. I strongly echoed with their point. Extremely important for sure, especially for the GCM model to specify the geomagnetic forcing. And our recent study basically indicated the mesoscale convection pattern can enhance the geoheating by 30% in average, so definitely it's not negligible. Ideally, if we can get a high-resolution convection pattern over the whole polar region in both hemispheres, that would be fantastic. All right, but today I'm not going to talk about mesoscale. I'm going to talk about larger scale, which is interhemispheric asymmetry. And as you know, on December 4th, 2024, a solar eclipse happened over the southern polar region, and which strongly reduced the ionosphere conductance, provide an unprecedented opportunity to study the ionosphere response and also the impact to the whole geospace environment. And here is the model we used, and regarding the solar EUV radiation, we implemented the EUV mask from Sebastian to reduce the solar radiation over the southern polar region, and in the Gideon simulation. And then about the MI coupling, we take actually 3 particular steps. First, we use the empirical model to drive Gideon, which does not change, does not influenced by the eclipse at all, just independently. Pretty much does not change that much. And to set up the RON in Gideon, then we get the Gideon standalone simulation. For that simulation, it only represents the solar irradiation reduction effect. And then we coupled the Gideon with the space-wide modeling framework through RIM, and then the RIM will solve the potential and also communicate with the MHD model and the ring current model. Then got a new output about both potential and particle precipitation, and this is step 2. And then since we got the particle precipitation and convection from the MHD model, from a space-wide modeling framework, we can implement the new updated convection pattern and particle into Gitten to see the feedback from the magnetosphere. So that's the 3 steps we are taking. And first, let's look at the Gitten standalone simulation, only including the solar irradiation reduction. So the top panel basically shows the IGS-TEC observation, and the middle panel shows the difference field. So after subtracting the 3-day average TEC observations and represent the difference from acquired time, you can see along the eclipse trajectory, the density got reduced for sure. But for observation, it includes everything, not just solar irradiation reduction. So you can also see some enhancement on the light side. This may related with the substorm, which happened to be close to the solar eclipse period. Then if you look at the simulation, since we only include the solar irradiation reduction in the Gitten standalone simulation, you will see the reduction of the TEC at a similar location as the observation. So roughly, this Gitten simulation reproduce the reduction in the ionosphere density. All right, and then next we look at the reduction in the conductance. The top panel is a reduction in the Peterson conductance, and the bottom panel shows a reduction in the Hall conductance. So in general, the reduction can be up to 10 sigmas. And so it's definitely not negligible. And then we feed this back, the ionosphere conductance into the magnetosphere, and then we got both the polar cap potential and current from the magnetosphere, and we compared those cases with and without eclipse in both northern and southern hemisphere. In the southern hemisphere, where the eclipse happened, you can see the solar eclipse actually increase the polar cap potential, because if you look, which may be explained as a current generator. If you look at the magnetosphere current generator, the reduced conductance will enhance the convection potential. And in the northern hemisphere, initially not too much difference, but after a certain time, you can also see some change as well, which indicate both hemispheres are connected. Then we look at the interhemispheric asymmetry for both polar cap potential, CVCP, and the total geoheating. And actually the eclipse reduce the asymmetry, which can be understood as the reduce of the conductance will make both hemispheres to be more symmetry, more symmetric. Because in the northern hemisphere is winter. If you reduce the conductance in the southern hemisphere, then it becomes more similar. And also the total geoheating, if you just look at the magnitude, the symmetry is also better. It's less symmetric. All right. Then if you look at the configuration of the magnetosphere, so here just the movie, shows the plasma pressure and also ion drift in the anti-sound direction. The difference may vary from moment to moment, but at a certain time, definitely they're not identical. That's the bottom line. They do cause some difference in the magnetosphere configuration. If just put one particular time, maybe, okay. Oh, I cannot, maybe I can stop at any particular time, make it clear. Okay, so then we summarize the difference by looking at the last close magnetic field line in the tail region. And between 8 UT and the 9 UT, the difference of those position can be different by 16 RE. So again, it's not negligible, depends on the time. All right, since we have the output from MHD model for both with and without eclipse situation, then we can use this MHD output to drive Gaten, which is step 3, like I mentioned about that. So now we move on to the step 3. We look at the feedback of magnetosphere to the ionosphere-thermosphere. So top panel basically shows the Gaten standard alarm simulation, and the second row basically shows the case when we include both the solar radiation reduction and the feedback from magnetosphere. So this feedback strongly enhances the polar cap, both anti-convection and the neutral wind. This here we show the neutral wind. So neutral wind got enhanced dramatically. And if we look at one particular location, the difference of neutral wind can be more than 100 meters per second. So certainly the feedback of magnetosphere can be important for the neutral dynamics. In summary, the solar UV reduction in the solar eclipse can cause roughly 30% change of TEC and the modified AMI coupling. And the magnetosphere, it change global configuration, and the X point location can be different by 16 RE. And the feedback from magnetosphere to the ionosphere is important for the ionosphere-thermosphere dynamics for sure. Thank you.
Dan?
Nice presentation. In the video you showed, I noticed there seemed to be more changes, or at least I could notice more changes in the tail rather than on the day side. Could you talk about that a little bit? Just about like what's driving that differential day side, night side?
That's a great question. Yeah, we also noticed that. Actually, I didn't show it in our paper. We quantified the last close magnetic field line in both day side and night side. And turns out the light side does show much difference in the day side. And there could be a couple of reasons. And one reason, maybe on the day side, the solar radiation conductance is dominated, so the influence could be relatively small. And on the lighter side, the change of the tail location may influenced by the wobbling of the magnetic tail as well. So the consequence could be more significant. Right?
All right, thank you, Yue. And I want you to stay there. We have 5 more minutes. We're perfectly on schedule. So at the end, we'd like to have a little bit of open discussion, including pretty much everything, but particularly toward the first half of the session. So like you commented earlier, so the modelers like you, ionospheric modelers like you, and in the audience there are magnetosphere and MI coupling modelers, particularly around. So now we have observations like what we saw earlier with a lot more accurate and better convection available. So are there something you can either take or compare to your modeling output for your own science, or do you think we still need more improvements in measurements? So that kind of feedback would be appreciated.
Absolutely. Yeah, I really appreciate the collaboration with Pierre and Toshi, and we love data for sure. Yeah, we need more data to help us to specify the mesoscale variation and in the global wide. That strongly improve the simulation, in terms of both spatial and the temporal cadence. Yeah, we need help from the observational community for sure. Yeah, like what I said, ideally, if we can get high resolutions anti-convection pattern high cadence in both hemispheres. That would be fantastic. I'm not sure, Bill maybe can come on. What's the timeline, or is when will it be feasible to get those kind of specification and publicly available for the community?
There, can you give the microphone to Bill?
So high spatial resolution in the northern hemisphere is, we can do that now. The cadence, we could update at a faster cadence, but it would only be part of the array that updates, really. And if you have a focus region like we did with some of the stuff with Cheng, that would work. You could have a higher cadence in a region. The southern hemisphere, I think it's going to be a while before we get more radars down there, and that's really what we need to improve the observations. We have a proposal in to put radars at the tip of South America, but I think it's pretty unlikely that NSF's going to fund that at this point. Other folks in the community aren't proposing new radars. China may put the radars in if we don't, so maybe we will get them. I don't know.
I'd like to hear from more modelers. So, for example, Bob Lysak, so things like what you do about ULF wave simulation, those things. So now we have pretty comparable level of time resolution flows like here. So are these enough to compare to your testing, your modeling, or do you think the observation need to come more to compared to your simulation?
Well, I think we need to make the simulations a little bit better, of course, always. Well, we're coming closer together with that, I think. I don't know if we're quite there yet, but we'll get there.
And also, Roger gave presentation earlier about the patch formation, things like that. So we have similar data set on the day set as well for showing the multiple flow channels, indicating multiple day set reconnections. So those are probably something we can compare to the high resolution measurements the MAGE team has. So do we think we are ready for that sort of thing now, or you think you will have any desire to, the radar or any other observation team so that you can take advantage of measurements?
I mean, definitely we should try to compare MAGE to some of the high resolution SuperDAR and to see. I mean, it's never going to produce individual flow channels in the right positions and locations, but if we can figure out a statistical way to do it in terms of statistical appearance of flow speeds and channel widths and whatnot, it seems worth doing. I also want to express that I would love to see more in the southern hemisphere because, so the most confusing part of all these mesoscale flows to me is which ones are conjugate and which ones are not, right? When you talk about a BBF in the tail, it's a tail reconnection, so presumably it's got a streamer on both ends of the field line. But when you talk about these mesoscale flows in the open field line polar cap, there's no reason for them to be conjugate at all. So when we talk about a high-speed flow coming from the polar cap towards the auroral oval, I'm very confused as to what that would look like in both hemispheres. Yeah.
Bill?
So I think that's one area where we could actually do something now. We do have radars that observe the cusp region in the southern hemisphere very well at this point, and northern hemisphere. And I think Ying did a paper last year where she actually had flow channels in both hemispheres roughly simultaneously. So.
All right, any other comments? If not, let's close the session. Thank you for your participation. I think this session went well with lots of questions. We were able to take actually all the questions for all the speakers, so that's very nice by taking advantage of workshop mode. So if you have any further feedback, please feel free to let us know. Otherwise, enjoy your poster session. Thank you.